All right, it's time for more tricky parts of calculus. This episode is about two of the most widely used functions in mathematics, the exponential function and its inverse, the logarithm. The exponential function exp of x is the unique function with value 1 at 0 whose derivative is equal to its own value, so that as its value increases, its rate increases just as sharply. Exp of x is also equal to a special number e raised to the exponent x. The number e can be characterized in a few ways. It's approximately 2.71828. Exp of x also satisfies the key additive-multiplicative property exp of x plus y equals exp of x, exp of y. I should have chosen different letters so I didn't have to say exp of x, but whatever. Exp goes to 0 as x goes to minus infinity, and as x gets larger, exp grows faster than any polynomial. Exp has an inverse called the log of x, sometimes written ln of x for natural logarithm. It's defined for x greater than 0. It satisfies the multiplicative additive identity log xy equals log of x plus log of y. It has derivative 1 over x and grows slower than any power of x. Now, every single professional in the sciences, technology, engineering, or mathematics is very familiar with these functions, but I challenge any of them to introduce these functions and prove that they have these properties to someone just learning calculus. It's not easy. I want to give several ways to approach these functions that are motivated, appropriate for students at the beginning of a calculus class, and involve actual proofs at the expense of having to work a bit harder. Hopefully, this is a useful service to the mathematical community because these proofs are rarely done or all found in one place. I'm going to take 2 episodes to do this. In a second episode, I'm going to discuss the actual history of these functions, which is fascinating and almost never covered, so you can see how people actually figured these things out. All right, let me begin with what I'll call method 1, which is to introduce e to the x through extension of exponentiation to all real numbers. It's probably the most sensible approach for students in terms of motivation, but actually it's the most work. So let's fix a number c greater than 1 as our base. If the base c is between 0 and 1, then c to the r equals 1 over c to the minus r. A natural context for this operation is compound interest. For integer exponents t, c to the t equals v is the value of an investment of $1 after t periods at the interest rate, which we usually quote as c minus 1 times 100%. And you can also think of the inverse operation, what we call the log to base c, as giving the amount of time until the investment reaches a given value. Exponentiation by rational exponents is defined to have the additive multiplicative property. So for example, c to the 1 over n is the nth root of c. What's hard is making sense of exponentiation on arbitrary real arguments. Usually a teacher or textbook will say something like, you can extend this operation by continuity to the real numbers. What I suppose this means is that we should define c to the x to be the limit of c to the q as q rational approaches x. That definition turns out to be a bit unwieldy since you'd have to prove that this limit exists and doesn't depend on the sequence. It turns out to be easier to exploit the fact that c to the q is increasing on the rational numbers, take that as a simple exercise, and define c to the x to be the sup, or least upper bound, of all values c to the q for all q rational less than or equal to x. Now we can appeal to one of the basic properties of real numbers, that every non-empty subset that's bounded above has a least upper bound, to know that this is well defined. This is a point of theory which is not usually emphasized in a calculus class, but it's what you need to make sense of extending exponents to irrationals. The thing is, now you've got to show that c to the x plus y equals c to the x times c to the y for arbitrary real exponents, and you also want to show that c to the x is continuous. The main point is to show that the limit of c to the 1 over n is 1 as n goes to infinity. The way to do this, and remember, we don't have access to the properties of the exponential or the logarithm, is to use a very nice algebraic inequality for dealing with exponentiation. So here's the key lemma for inequalities involving exponents. Let's take a and b to be real numbers with b greater than a greater than 0. Then for n a positive integer, we have the factorization b to the n plus 1 minus a to the n plus 1 equals b minus a times b to the n plus ab to the n minus 1 plus a squared b to the n minus 2 plus dot 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 plus a to the n minus 1b plus a to the n. This quantity here is n plus 1 terms, each of total degree n in a and b, which, since a is less than b, lies between n plus 1 a to the n and n plus 1 b to the n. So we have that inequality with star equals b to the n plus 1 minus a to the n plus 1 over b minus a. So returning to the limit c to the 1 over n, if you apply the left-hand side of this inequality with b equals c to the 1 over n plus 1 and a equals 1, we get c to the 1 over n plus 1 minus 1 is less than c minus 1 over n plus 1, which goes to 0 as n goes to infinity. And of course, c to the 1 over n plus 1 minus 1 is greater than 0 since c is greater than 1, which shows that c to the 1 over n minus 1 is squeezed between two quantities that go to 0. And so this goes to 0 as n goes to infinity. Now, showing c to the x plus y equals c to the x times c to the y is partly a matter of comparing the sets of rational numbers involved in the definitions, any t rational less than or equal to x and s less than or equal to y, when some will give a rational number less than x plus y, which gives that c to the x times c to the y is less than or equal to c to the x plus y, though it doesn't work the other way. For the other inequality, you have to use more of the acrobatics of the sup property. Fix epsilon small and take a rational q less than x plus y, such that c to the q is within epsilon of the sup. That can always be done by the definition of the sup. Now, for any delta, no matter how small, there's always t rational between x and x minus delta over 2. That's the density of the rationals in the reals. And the same for s. So we can find t plus s greater than q minus delta. Continuing the proof, c to the s plus t is at least c to the q times c to the minus delta. So as long as c to the minus delta is closer to 1 than epsilon over c to the q, which can certainly be done because c to the 1 over n goes to 1 and c to the q is increasing on rational exponents, then c to the s plus t is at least sup b minus 2 epsilon. That's true for any epsilon. So c to the x times c to the y is at least c to the x plus y, and then we have both inequalities, so they're equal. And now continuity for real arguments just uses the same limit again. Yes, this is the kind of argument that's usually reserved for a course in real analysis, but that's how it's done. Note that the work was really in showing c to the 1 over n goes to 1. Let me pause here and mention a different approach, which I'll call method 2, which will come up later. Suppose instead of extending exponentiation, you wanted to look for functions satisfying the additive multiplicative property f of x plus y equals f of x times f of y. Then it's not hard to show that f of q equals f of 1 to the q for all rational numbers q. If you insist as a hypothesis that f is continuous, it must be that f of x equals f of 1 to the x as defined above, or else f is identically 0. Here's the proof. F of x equals f of x times f of 0 for all x, so either f is identically 0 or f of 0 is 1. And as long as you have any non-zero value, no f of x can ever be 0. For that matter, all the non-zero values are positive since f of x equals f of x over 2 squared. Then it's clear what all rational values must be in terms of f of 1. And if f is continuous, then because any real number x can be approached by rationals, its value must be the limit, or in particular the sup we used before. But you have to impose the continuity because it turns out there exist pathological discontinuous functions with the additive multiplicative property that are not the exponential that can be constructed using the axiom of choice. I'll include a reference in the description if you're interested in how this is done. All right, so we managed to extend exponentiation continuously to the reals, but what about differentiation? With the additive multiplicative property, when we try to compute the derivative of c to the x, the limit quotient looks like c to the x times the limit c to the h minus 1 over h, which tells us that as long as this limit exists, the derivative is proportional to c to the x. Now, it's sometimes simply asserted at this point that this limit does exist for any base c greater than 1, and e is the base that makes this limit 1. But it's actually possible to show somewhat directly that this limit exists as long as we first talk about the number e. So many lecturers pause here to give a definition of e as the limit of 1 plus 1 over n to the n. 1 plus 1 over n to the n represents the amount of money you would have at the end of 1 year if you invested $1 at time 0 at the pretty incredible rate of 100% interest compounded n times. So 1/nth of the yearly rate is compounded n times throughout the year. As n goes to infinity, this is called continuously compounded interest. This question of continuously compounded interest was first posed by Jacob Bernoulli in 1683, and it's not obvious that this procedure has a limit, but indeed it does. Usually it is convincing enough for a calculus class to plug in some large values of n into this formula in a calculator, or maybe they're putting it into Python programs these days. I don't even know if students use calculators anymore, but you can see that the value does not seem to be increasing more than about 2.718 or so, even after millions of terms. But in my view, we have an assertion that requires a proof, namely that the sequence S sub n equals 1 plus 1 over n to the n converges. So let's prove that. We can use a similar strategy as used by Archimedes to find the area of a circle, see my episode 3, by showing there's a unique number bounded between an increasing sequence and a decreasing sequence. We have to show that the sequence S sub n is increasing, and these numbers are bounded above by a decreasing sequence T sub n, which will be 1 minus 1 over n to the minus n. So you could play around trying to show that the sequence 1 plus 1 over n to the n is increasing. It's not obvious. 1 over n is getting smaller, so 1 plus 1 over n is getting closer to 1, but it's being raised to a higher power n. But it does fall out of the key inequality that we proved before. Take b equals 1 plus 1 over n, which is greater than a equals 1 plus 1 over n plus 1. Then the right-hand side of the key inequality says this. The denominator is 1 over n times n plus 1, so multiplying by that on both sides and subtracting the right from the left gives the inequality that we want. Now, note that 1 plus 1 over n equals n plus 1 over n, which is equal to n over n plus 1 to the minus 1, which is equal to 1 minus 1 over n plus 1 to the minus 1. And therefore, S sub n times 1 plus 1 over n, which is equal to 1 plus 1 over n to the n plus 1, equals t sub n plus 1, which shows that S sub n is less than t sub n plus 1. You can show that t sub n is decreasing by applying the key inequality on the left with a equals 1 minus 1 over n, b equals 1 minus 1 over n plus 1. That's another exercise. I find this a lot easier than trying to show that 1 plus 1 over n to the n plus 1 is decreasing when written in that form. Now it's not hard to show that every S sub m is smaller than every t sub n. So what we have is an increasing sequence bounded by a decreasing sequence, and they get as close as one likes. So there is a unique number between all of them that's their common limit, which we call e. Note that the rate of convergence is slow. E is between S sub n and T sub n plus 1, which is equal to S sub n times 1 plus 1 over n. So the error in approximating E by S sub n is about E over n. So you need to go to about the 3 millionth term or so to know that you have 6 decimal digits of accuracy. But the advantage of this approach is that now you can compute the derivative of e to the x. We have to compute the limit e to the h minus 1 over h as h goes to 0. Let's compute this limit along the special sequence h equals 1 over n. So the limit is n times e to the 1 over n minus 1 as n goes to infinity. Note that for any fixed n, we have n times s sub n to the 1 over n minus 1 is less than n times e to the 1 over n minus 1, which is less than n times t sub n to the 1 over n minus 1. And the outer two expressions both have limit 1 as n goes to infinity, so the limit with the number e is squeezed in between, and it follows that e to the x is its own derivative. Okay, if you want to be strict, I haven't actually shown that the key limit exists, just that it goes to 1 along a particular sequence. If you really want to compute the limit e to the h minus 1 over h properly from our definitions, the best way is probably these 3 steps. 1, show that the limit 1 plus x to the 1 over x as x goes to 0 exists, which we've already shown for the single sequence, x equals 1 over n. 2, use theorems about continuous increasing functions to introduce the inverse function, the logarithm, and show log of xy equals log of x plus log of y. Then, in step 3, you can compute the limit e to the h minus 1 over h by substituting x equals e to the h minus 1, so h equals log of 1 plus x, and the limit becomes the limit as x goes to 0, x over log of 1 plus x, which is the same thing as the limit of 1 over log of 1 plus x to the 1 over x. This is 1 over log e, which is equal to 1. To show 1 plus x to the 1 over x has a limit, which is certainly e if it exists, you use that we already know the limit 1 plus 1 over n to the n. Note that it's harder to prove that 1 plus x to the 1 over x is monotone if you don't already know how to differentiate exponential functions. But if x is greater than 0 and small, then there's some n such that x is between 1 over n plus 1 and 1 over n, and then we can certainly say that 1 plus x to the 1 over x is between 1 plus 1 over n plus 1 to the n and 1 plus 1 over n to the n plus 1, since, for example, x is less than 1 over n and 1 over x is less than n plus 1. As x goes to 0 from above, n goes to infinity, and both outer limits go to e by what we've already proved. We have to argue separately for x negative. If x is less than 0, let t equals minus x, and then 1 plus x to the 1 over x equals 1 minus t to the minus 1 over t, but that's equal to 1 over 1 minus t to the 1 over t, which is equal to 1 plus t over 1 minus t to the 1 over t, which is equal to 1 plus t over 1 minus t to the 1 minus t over t times 1 plus t over 1 minus t. And now the first factor goes to e and the second goes to 1 as t goes to 0. Note that at this point you can also show that for any real number k, the limit 1 plus kx to the 1 over x goes to e to the k. Just substitute u equals kx, so the limit is 1 plus u to the k over u. This is another possible definition of e to the k, often given as the limit 1 plus k over n to the n, which can be useful. So step 2 that we needed was introducing the inverse function. We need the continuous version of the inverse function theorem, namely that a function that is continuous and strictly increasing has continuous, strictly increasing inverse. I guess I felt like stating this theorem on open intervals. This theorem uses the intermediate value theorem for continuous functions. We know x is continuous, defined for all reals, goes to infinity as x goes to infinity by the Archimedean property, and goes to 0 as x goes to minus infinity, since these are the reciprocal values of x at minus x. So there's an inverse we call the log that's increasing, continuous, and defined on 0, infinity. The multiplicative additive property comes straight from the definition, and also that the intermediate value theorem guarantees that for all positive a and b, there are x and y such that x of x equals a and x of y equals b. Note that these are powerful theorems about continuous functions that are usually not proved in a calculus class, and were only stated and proved carefully long after the development of exp and log historically. If you want to take derivatives of exponential functions with a different base, the simplest way is probably to come at this another way by saying if f of x equals e to the kx for some fixed k, then by the chain rule f prime of x equals k e to the kx, and also f of a plus b equals f of a times f of b, and f is differentiable, so f of x equals f of 1 to the x, which is equal to e to the k to the x. And now every c greater than 0 is equal to e to the k for some k, again by the intermediate value theorem. So d by dx of c to the x equals k e to the kx, which is equal to log of c times c to the x by definition. Once you have the derivative of the exponential function, you can get everything else. You can use L'Hopital's rule to show that e to the x grows faster than any polynomial. You can compute all the higher derivatives of e to the x, and they're all the same, at 0 to find its Taylor series centered at 0. And you can argue, as we did in episode 4, to show that e to the x is actually equal to its Taylor series on the whole real numbers. The inverse function theorem will say that the derivative of its inverse, the logarithm, is 1 over x. Now let's look at a totally different presentation of the exponential function, starting over from the beginning. Suppose instead of being concerned with exponentiation, you took as the defining property the differential equation y prime equals y with y of 0 equals 1. That signifies exponential growth with exact constant of proportionality 1. That is, we'd like to define a function x of x to be the unique solution of this equation. This is a sensible thing to do because there is a theorem that says that such first-order equations with an initial condition have a unique differentiable solution, at least for x near 0. This theorem is sometimes called the Picard-Lindelof theorem. But this is almost never done in a calculus class because this existence and uniqueness theorem uses a lot of theory, not only the fundamental theorem of calculus, but also the Arzela-Ascoli theorem or some fixed point theorem. I just want to comment that you have to use the full strength of the general theorem for first order equations and not the stronger and easier theorem for first order linear differential equations, because that theorem uses the properties of the exponential to construct a solution. All right, but if you were willing to accept that there is a unique differentiable solution to the equation, then you can get the additive-multiplicative property right from the equation as follows. If we shift by some amount z in the interval of definition and look at f of x equals x of x plus z, this function satisfies f prime equals f with f of 0 equals x of z. But so does the function g of x equals x of z times x of x. So these functions must be identical. And through repeated application of shifts, it's clear that x of x is defined for all real x. The additive multiplicative property identifies this function as being the same we think of as exponentiation, with e defined to be x of 1 as the base. If you don't want to rely on a theorem about differential equations that requires more theory to prove, you could construct a power series solution to the equation. This technique is usually done in a second semester of calculus or differential equations course, but there's actually nothing wrong with introducing the technique now. Just suppose that y of x equals the sum a sub n x to the n solves y prime equals y, as though you were seeking a polynomial solution of unspecified degree. Then formally differentiating term by term gives the recurrence relation a sub n plus 1 equals a sub n over n plus 1, and the initial condition gives a sub 0 equals 1, meaning you get a formal solution by taking a sub n equals 1 over n factorial. So there are infinitely many non-zero coefficients, and you have a formal power series solution. That's just algebra. The advanced part is to show that this defines a function on the real line by showing it converges using the ratio test, which is an argument I gave in the previous episode. I prefer this exposition to starting from the power series as a definition, since it shows a natural concern, the differential equation that gives rise to these coefficients. From here, you can show, using the binomial theorem and rearrangement of series, that y of x plus z equals y of x times y of z, which was also done in episode 4, or you can appeal to the differential equation as in the previous method. The number e here is defined to be y of 1, which is now given by the convergence series 1 plus 1 plus 1 half plus 1/6 plus 1 over 24 plus ... all the reciprocals of the factorials. This series converges much more rapidly than the sequence 1 plus 1 over n to the n, which you can see by comparing the error with the geometric series. Now you get 6 decimal places of accuracy just by summing up to 1 over 8 factorial, since 9 times 9 factorial is already more than 1,000,000. Despite the fact that you have to introduce the concept of power series, this is probably the best approach to the exponential function at the beginning of a calculus class. Of course, if you wait until you have the theory of integration, you can start completely differently. All of the power functions have power function antiderivatives except x to the minus 1, so you define a new function, the log of x, as the standard area under a hyperbola, or the integral from 1 to x of dt over t. This integral defines a continuous increasing function for x greater than 0. The multiplicative additive property is a simple consequence of change of variables under the integral. From that you get that the log is not bounded above or below because you can check the values at the powers of 2, for example. Now, if you have the fundamental theorem of calculus, you can see that the log is differentiable with derivative 1 over x. And then the inverse function theorem will say that the log has an inverse whose derivative is 1 over log prime at log inverse of x, which is log inverse of x, so the log inverse solves y prime equals y with y of 0 equals 1. Or you can establish that the inverse of log satisfies the additive multiplicative property by the reverse of the argument that we used before when we were introducing the logarithm as the inverse of the exponential function. Here, e equals log inverse of 1 is the value at which the area under 1 over x is 1. Now, the limit 1 plus x to the 1 over x was very involved to compute from the exponential side, but from this side, it's a lot easier to show that the limit of log of 1 plus x over x is 1, since you can compare areas by identifying log of 1 plus x as the area under the graph of 1 over t. It's clear that the area is between rectangles of area x and area x over 1 plus x. Dividing through by x and using the squeeze theorem gives the result. The same can be done for log of 1 plus kx to show that e to the k equals the limit of 1 plus kx to the 1 over x. So that gives you several ways to establish the properties of the exponential and the logarithm. Let me know in the comments if there's anything I missed or if you find this sort of material useful. In the next episode, as promised, I'll give a very different exposition of these functions based on how they were actually introduced historically. It's so interesting and few people ever see it. I hope you'll be back. Thanks so much for watching.